That's fine. Well, it's great to be with you this morning. I'm John Havlin, if you haven't figured that out. I've been at NC State about 24 years. I came here from Kansas State to be department head of soil science here at NC State, and then after 10 years of that misery, being an administrator, I said, no, I love teaching way more than that, and so that's what I've been doing since. I have a very heavy teaching load. I'm about 5 years from retiring. I know it doesn't look like that, but I'm almost 70, and I'm going to be doing this for another 4 or 5 years and then hang it up. But I have a heavy teaching load. This is spring break for the students, not for us. And so I'm on a 7-city whirlwind tour this week doing these kinds of programs. And I've done a lot of Master Gardener programs in the counties throughout the state. Matter of fact, I have 2 more this week to do. This is a really important topic for you. I'm not criticizing the organizers, but to spend an hour and a half on the most important subject that you'll ever need to know about is not enough time. So I'm going to go through some things that are really fast, and you probably, hopefully you'll get it, and sometimes you don't. But let me just ask you, and I can come back. We can have another session sometime down the road to refresh, right? Yeah. Maybe expand on some other things that you're more interested in and that I didn't cover. So we can do a 2-way negotiation on the next steps. But when you find, you've got a piece of land somewhere, right? Yeah. And it's how big? Just less than an acre. Less than 5, more than 5. Okay, more than 10. Okay. So most of you are pretty small. So you're dealing with inputs on a 1,000 square feet basis. So later on at the end, we may not get to it, I'm going to have some math. Here's the soil test report, and it's recommending 4 pounds of nitrogen per 1,000. And the lab says, well, I want you to put 25 pounds of 1507. Well, if you don't know what that means, then, why bother taking a soil test? And then you say, okay, I know what 1507 is. I go down to Home Depot and look at the shelf, and I see all these fertilizer bags, and none of them are 1507. Now what do I do? Well, you got to know how to take the 4 pounds of N per 1,000 and convert it to number of bags, whichever one you select. And that's a little bit of math. It's not complicated. I'm looking at the relative ages of you. I'm not going to say any. But you know how to do this math. Your children, however, struggle massively. They do. I've been doing this for 42 years. Teaching undergraduate soil fertility for 42 years. And sorry about that. And in the last 15 years, the quality of our children coming out of K through 12 is outstanding. They are smarter than when I was in their chair. But they don't want to work. They don't want to do that. They don't want to do math. That's too hard. And chemistry, we used to have advanced chemistry in high school when I went through high school. Now they have general science. All that other is gone. So they don't know chemistry very well. You got to know what a cation or an anion is, don't you? To do what you want to do. You're going to be master gardeners. I think that's quite an accolade. I really do. Hopefully sometime down the road, after you've got the experience and all that, all the wonderful knowledge you're gaining from this program, you'll be on a radio show some Saturday morning. And they'll be interviewing you, call-in questions, right? Master gardeners do that. Well, somebody's going to have a soil test on the phone. Go, what the hell does this number mean? And if you don't know, it's not good. So when you looked at your piece of land and you said, well, I want to plant some broccoli or some tomatoes, and you just got the seed, you just started it in the greenhouse and you transplanted it, or you put the seed in the ground, you walked away, And let's say we were talking about sweet corn, and you got 7 ears. You put 250 plants, seeds in the ground, but you got 7 ears. Was that successful? Can't hardly freeze that, right? So there was a problem. And you don't put seeds or plants in the ground unless you have a soil test. And if you don't have a soil test, if you have a soil test but you don't know how to interpret what the report is, because they don't tell you everything that each one of these numbers means. So if you just take a gander at this sheet right here, it says soil test. The backside says plant analysis, soil test. And just look at A. Now, is there a lot of boxes with a bunch of numbers? A bunch of abbreviations, CEC, BS. That's not the quality of this presentation. If you don't know what those mean, then you're not a master gardener. As simple as that. So I have put a way of explaining this complicated report in such a way for you to walk out of this meeting and know what those numbers mean. Fair enough? That's what you want. That's what you need. All right. So the first thing we want to do is, first of all, understand what kind of material we're dealing with. On the planet, we call, there's a nomenclature system for plants and animals, genus, species, family. Remember all that? You don't know the name, a scientific name for all the plants and the insects and birds and all that. We have the same kind of nomenclature system for soils, except the big umbrella, there's 12 soil orders, major soil types on the planet. And in North Carolina, we have this guy called an ultisol. Now, soils are formed from rocks, either blown out from a volcano or deposited from ash. Those are volcanic soils, or the earth uplifts and the rocks are exposed to the atmosphere, oxygen and water. Water has a slight pH, acidic pH, 5.6, and that little bit of acid starts to dissolve the parent rocks into their cations and anions. Over millennia, we get a soil formed. This guy in the southeast dominates our southeast because we have lots of water and temperature. It's pretty warm, right? You blindfold me and drop me off on an airplane to Raleigh, North Carolina. I get out of the airport, and the first thing I do is say, what kind of climate do you have? And, well, it rains a lot, and it's pretty warm. I say, well, okay. I know you're going to need lime. I know you're going to need phosphorus, potassium, maybe calcium, magnesium. The micronutrients we don't worry too much about. If you drop me off at Denver, Colorado, well, we don't need lime. Those soils already have lime in them, naturally. They're high pH soils. So my micronutrients are more problematic, but calcium, magnesium, potassium, generally not a problem. So understanding what you're dealing with is really important. This is we call this a highly weathered soil. And it's the second most weathered soil of all of them. Sorry, I'm going to walk across this every now and then. I have a tendency to dance around the classroom, kind of keep students awake. I won't throw any erasers. Every now and then we'll give a quiz. Anyway, the most weathered soil on the planet is called an oxisol. Where do you think they might be if high rain and temperature is related to... Tropics? Yes, tropics. So what countries can you think of?
Ecuador.
Brazil, yes. The Amazon, yes, you got it. Those soils there naturally with a pH of 3.5. Very low phosphorus, very low calcium, magnesium, potassium. I mean, it's classic textbook.
Is that because it gets rained out?
Because a lot of water moves through. And I'm going to shorten this up because I just don't have the time. But it's all the water moving through and carrying those basic cations below the root zone. So anyway, we're going to move along. Now on your piece of land, all those soils are not the same, called the same. There's differences. But every one of these soils, this is a North Carolina photo, every one of these soils in the Piedmont are altisalts. They are genetically related, but there are some differences, some minor differences that only a soil scientist would care about. But for you, there are some differences. Anyway, so basically what happens, to answer your question, what happens to these nutrients is I have this removal of, these are cations, right? I put them in blue, which means they're good guys. They're essential plant nutrients. Don't sing your song yet. They're essential plant nutrients. And as a result of these guys moving down through the profile over millennia now, we still have calcium, magnesium, potassium in our soils. It's not devoid, but it's lower than it would be at a higher pH soil like Colorado. And we have an elevated level of this cation called aluminum. That's an acid. And that's why we need to lime, to raise the pH and reduce this and increase these. So we're going to show you how that works. And as a result of more of this acid and less of these bases, my pHs are acidic. They're all acid soils. You're going to lime everything you're going to grow except for what? Blueberries, azaleas, hydrangeas. So you got to know what the optimum pHs of your plants are, and usually you can look that up. Just Google what's optimum salt pH for blueberries, and they'll say, well, we like to see them around less than 5. And so down in Pender County and those sands out there, irrigated sands, why there's a huge blueberry production region, and it's growing massively. It's one of the fastest growing crops in North Carolina. And then phosphorus. That's an essential plant nutrient. Now, majority of our soils are well endowed with this nutrient, and it's not because when humans first started scratching the soil surface in North Carolina, we found a lot of phosphorus in these soils. It's because of past management by humans that increased phosphorus level in these soils. And the first management thing that happened was tobacco. So we had a lot of Piedmont soils, eastern North Carolina soils growing tobacco, right? 1600s, 1700s, shipping it back to England and wherever. And we did use fertilizers, believe it or not. And they would, in the last 100 years, since about early 1800s, they would use this product called a 399. I can't remember what they called that, but that was the analysis, 399, which is 9% P2O5 and 9% K2O, potassium. Well, and they would put a ton of it on their acre. Well, 9% of 2,000 pounds is how much? 180 pounds. So you put on 180 pounds of P2O5 every year for 40 or 50 years, your soil test phosphorus levels are going to go through the roof. And today, in the last 40 years, what have we been doing? Mostly eastern North Carolina. What have we been doing? Animal waste. Animal waste. And so we put 10 tons of hog or chicken waste on our fields, and that meets the nitrogen requirement of the intended crop, but it's 3 to 5 times the waste rate to meet the phosphorus requirement. So we're putting 3 to 5 times as much phosphorus that crop could ever use. So soil test levels have gone through the roof. But out here in the west, not here, but if you go west and talk to the Christmas tree growers, the vineyards that have never had any of these products historically, waste or tobacco, they're all low phosphorus. They're all low phosphorus. So anyway, that's the point. So let's quickly move on. There's a real quick description of what a soil profile looks like. You don't get to see this unless you dig a hole, dig a pit. And so we're supposed to have a nice layer of organic material on top, partially decomposed residues. That's a really important part of your soil because it has a lot of, whoops, I keep messing this up. It has a lot of pore space, which when it rains, a lot of water infiltrates rapidly and then can get into my profile, which I can use that water later during July and August when I really need it. And it has a lot of nutrients in there. And then the A horizon, notice it's dark, so these are a lot of high organic matter containing layers. And that's what you want to create. When you found this piece of land, you probably didn't see these. Because past farming practices, it's not the farmer's fault, it was just the way, the technology that we had back then. These soils eroded away. These topsoils eroded away. Most of our farmers in the Piedmont are farming subsoils. That's what's on the top, subsoil. That's what you're farming.
Like after they got finished building our houses.
Yes, but you can build this back up. And in a small area, you can import carbon. I'm going to talk about that real quick here in a minute. You can import carbon to get that to happen. That's what you want to do. I'll talk about that more in a minute. But anyway, most of your nutrients to your plants are here. Now, roots do go down into this B horizon. It's more clay. And when I soil sample, I'm soil sampling right in here. I'm not sampling down here. It's too hard to get the probe down in there. You guys have soil probes that they can have access to. If you have one of these nice fluffy surface 8 inches, that's great. You can get that little hand probe in one of those. But if it's this, you can't get that hand probe in 3 or 4 inches. You just don't have enough oomph to get it down there. So you got to have a hammer probe. Do you have a hammer probe?
Yeah, we have the long one.
Slide hammer.
And it's got the cutouts for slide.
Okay, good.
You know what we're dealing with.
I didn't bring one today, but we can talk about that later. Anyway, that's the B horizon. So it finds a lot of roots do go down here and find some water during July and August when it needs it. This surface might be dry, but it finds enough water. When the plant wilts, then you know it's not finding enough water down there. You know that. Anyway, but it doesn't find a lot of nutrients down here. And so we're really simply managing that surface foot or so of soil for nutrients. Okay. Oops. What did I do? All right. So again, just keep in mind, depending upon the crop you plant, you got different rooting depths. Carrots, beets, radishes, those that have very shallow rooting depth. They can't send roots down there to find that water. So you got to make sure that you've got enough water going down. And if you're in cover cropping, inter-row cover crops, which helps you build up that organic matter I was talking about, they use water and nutrients, so you got to account for their use of water and nutrients. Oftentimes we don't do that with the cover crop, but they use water and nutrients we have to account for. Anyway, and just be sure that when you have this clay subsoil, unless you're in a sand, I've been working with the vineyard growers for the last 15 years in North Carolina. This is a sandy soil, 2 meters of rooting depth from a wine grape plant. We don't have that. That's not what we're dealing with. We're dealing with this. And those roots don't go any deeper than 24 inches at a maximum. A lot of times only 20 inches. And so that's the depth that we're managing for that crop. And that's likely. All right, let's talk really quick about water. Your soils have a texture. And texture, and you can ask your agent about the soil survey manual, and they can find your soil or your plot of land in this book called the Soil Survey Manual, or you can get it online. It's a PDF file, it's free. And you can find your soil and it'll say what texture it is, and that's just the percentage of sand, silt, and clay particles on a weight basis. So if I have a volume of soil, about 50% are the solids and 50% are air or water. The spaces between the solids, called pore space. And when I'm managing water, it's the water in that pore space that I'm concerned about. Do I have enough? Do I not have enough? At what point do I need to irrigate, et cetera, et cetera. So again, sand, silt, and clay, the sand particles are big. You can usually see them. Just think about a beach, sand. There's different sand sizes, but and then silt, as you can see, the relative size, and then clay, are just little teeny guys. But those clays are where the engine is for nutrients and water holding capacity. You do want some clay in your soils. And so if I mention the influence of texture on some soil properties, do you know what infiltration means? Moving into. When it rains, you want the water to move into the soil. And then you can see if I have a sand, oops, I'll get this. If I have a sand, my infiltration is high. That means I tease my students a lot with this analogy. You're on the beach. You like to go to the beach? Well, the kids do anyway. And they always take a few items with them to the beach, right? And I say, well, what are those? And I'm expecting, sunscreen. And no, it's a cooler.
Yeah.
And what's in the cooler? Yeah, and so I said, all right, so you've had 11 of them, and you got to get up and you got to go into the ocean for a few minutes, right? And on the way, you grab that 12th beer, and of course you've had 11, so you fell down. On the beach, what happened to that spilled beer? It goes right in, right? It goes right in. That's sand. That's right. Oh, gosh darn it. That's that guy. Infiltration. Okay, now if you were at a clay beach, what would happen? The beer would run off, right? Doesn't infiltrate. You wouldn't want a clay beach. I don't know if I'd want to do that, but if you did, why the infiltration rate's really low, and the beer would run downhill. And so, depending upon your texture, I have high infiltration if I have a sand, and high infiltration rate, which means low runoff. When water hits the soil surface, you only got two options. It either goes in or goes away, runs off. And it's the runoff that caused the soil erosion in North Carolina, the degradation of all of our soils, dominantly in North Carolina. So again, when infiltration is high, runoff is low. It's just the opposite. Percolation. Water's already in the pores, but it's still moving. It's moving with gravity. And the pores have to be full of water before that percolation. But that percolation is an important property to get water down there, so when my roots go down to that 2 or 3 foot zone, they find that water during the high temperature, high ET periods. Anyway, water holding capacity, you can kind of see the same idea. Sands don't hold much water, I'm going to show you that, but clays hold a lot of water. Okay, but how much of that water in those pores is actually plant available is different. Now, there's more plant available water here than there is here, but there's actually more plant available water in this guy than there is here. And so if you have a good mixture of sand, silt, and clay, that's called a loam soil, it holds most plant available water. Anyway, so let's just take a look at plant available water real quick. Here's my clay particle. Water molecules are charged. They're polar. They have a positive end and a negative end. Remember that? Anyway. Okay, very good. So the negative charge in here attracts the positive end of the water molecule, and the water molecule sticks to the clay surface. And that's a really strong bond. And then, because they're polar, then the next water molecule sticks to the negative end of the first layer of water. And on and on and on. You can see I'm building it up. The plant cannot pull this water out of the soil, because the attraction for that clay particle to that water is so tight that the plant can't get it away. So I can take a dry soil and still has water in it. It's just not plant available. My plant will wilt. And so that's called, the amount of water stuck to that clay is permanent wilting point. And that my plant starts to wilt. And then I keep building water up until all the pores are now full, and gravity now is a force that is stronger than the attraction of the water molecules out here for that clay particle and all the other water molecules that the water moves down with gravity. Gravity now is a stronger force. Plants do not take out this water because plant roots need oxygen to do their job. And so if you have no oxygen, the pores are all full of water, the plant dies because it just doesn't have any oxygen. Okay, so you need water between these two levels. So again, let's just take a look. How much water will your soil hold? And I got sand, silt, and clay. I added 10, there's 100 mils of soil, 100 mils. I put 10 mils of water in there, in each of those soils. This one went down to here, but the clay only went down to here. So which one holds more water? The clay. Because in order to wet the soil down here, I got to add that much more water. So another way to look at it is if I filled up the entire container with water, pores full of water, it would take 40 mils, clay would hold 40 mils, sand only 15. So when I have a sandy soil, some of you might have a river bottom area that's sandy soil, I don't know, they're here in the Piedmont. My son lives on one. My outlaws live on one, sandy soil. And it dries out during the summer where he has to irrigate pretty frequently. So if you have a situation where this is all the water, all that it will hold, then I'm going to have to irrigate more frequently.
So is that the saturation point? That's the saturation.
Yes, all the pores are full of water, yes. Anyway, so let's keep moving. So this is the classic diagram that relates the water content. This is inches per foot of soil. So this is 1 inch of water in a foot of soil depth. That's 10%, right, on a volume basis. Okay. 1 inch out of 12, it's less than 10%. Anyway, so this is the water content at permanent wilting point. This is the water content at field capacity. That's where all the pores are full of water, but the drainage is stopped. So there is some air in those pores, but they're pretty full. Plants grow at field capacity, but if I added more water above field capacity, they don't grow as well because of the lack of oxygen. Anyway, you get the idea. So the difference between these two is the amount of available water. So how many inches of water do I have in the sand? Plant available water. Difference between that point and that point is about 1 inch, right? 0.8 of an inch. How about the clay? What is it? It's about 1.5 inches. There's more plant available water in the clay. But how many inches are in this loam? About 2+ inches. So there's more plant available water in the loam. It's because there's less clay and they're hanging onto that water with less tension and the plant can get it away in the loam. So again, when you bought your garden soil or your plot of land that you're going to be working with, you probably didn't think about that, did you? No? Did you look at the soil survey manual before you signed on the dotted line, wrote the check? That's the first thing you do. But we can't go back.
So it's a lot easier to overwater in a clay soil.
Yes. Yes, it is. Yes.
Essentially, the clay is sucking the water away from the roots of the plant.
It can at that low water content. Yeah, it hangs on. That number of molecules next to the clay is a lot thicker than in the sand because of the char. Anyway, it holds more, clays hold more water, but when I start to add water, again, the infiltration rates are really slow, so runoff is generally greater, so you got to add it very slowly, little bits at a time. Let it drain in, add some more. Don't add it before evening, right? Why?
Evaporate.
No.
You don't have more time to infiltrate.
What happens during the night if I irrigate and I wet all my leaves?
Bacteria, fungus, diseases.
Increased disease pressure. You do it before the sun comes up or early in the morning. So when the sun comes up, it dries those leaves out, reduce. Anyway, you get the idea. And it holds a lot of that water. Again, it's got more plant available water than the sand. Now this sand is very porous. It infiltrates, and if I just add a lot, well, I can get all kinds of water to go in and move right on by. move right on by, and I don't want that. So I'm actually adding just little bits of water to my sand too, maybe a little bit more than the clay, but I'm still putting it in smaller doses so that I don't over water that sand. It'll all go in, but I might have too much. Anyway, you get the idea. So, and then of course you understand I'm gonna not add the same amount of water in the spring as I do. Oh. All right, you got that. Anyway. So I just want to let you know what the rainfall is in general. This is 50-year averages in eastern North Carolina. And you can kind of see inches of rainfall, pretty consistent. Now, I know we have years where we have this huge amount in September when the hurricane blows through, and this year we had a lot of water, didn't we? There were counties that had over 100 inches of rainfall when their normal rainfall is 50 or 45. Anyway, you get the idea. And so ET, you know what ET is? Sorry?
Going back to this slide about the irrigation inches, can you just define spray heads and rotor sprinklers?
Say that again?
Down in
There's some fine print
Blue,
on
blue lower right.
The difference in its.
Oh, that's the kind of nozzle size. So if you have a sprinkler system, if that's what you're doing, then you need to measure what's the output. And so I put the water device, collecting device, turn my sprinkler on for an hour and see how much water came out. And most sprinkler heads, it's 2 inches of water an hour. And that might be too much for a clay soil to infiltrate.
And rotor sprinklers would be the kind that you would have.
I would measure that, yes, I would measure that water the same as any system. When a landscaper puts in a lawn irrigation system, and you put some nozzles out by the garden space, they set the timer and they never measure anything. They set the timer and walk away. And so if the timer's not working well, it's raining outside, the sprinklers are on. So it's really important to measure that. And then adjust your timer or your nozzle sizes to shorten up that output. And so it's just fewer gallons, 2 gallons per minute or whatever, smaller nozzle orifice. Your extension person here knows that very well. She's got that. She's got that down. Anyway, ET, what's ET? We all saw the movie, right? That's evapotranspiration, right? That's the sum of the water being taken into the roots, up the stem, out the leaves, plus the water being evaporated from the soil around that one plant. It's the sum of both water losses. Because I get evaporation from the soil surface, right? Plus water moving up the plant, out the leaf. That's ET, evapotranspiration. And it's pretty high in the summer, yes? And, well, it isn't too high down here. And so soil water content is pretty high when I don't have the plants using it. That makes sense, right? It just says that during this period of time when I have high soil water and no ET, I got water moving through the profile. I have drainage. I have percolation. That's another word for drainage. Got water moving through the profile. We don't measure nitrogen in soils because I've put nitrogen on my field here. I've harvested here. There's some nitrogen left over that the crop didn't use. But during this period and this period, with all that water moving through, all that nitrogen went right down. And so it's not there by the time I need to use it for the next year. So we don't even bother to measure it. So to increase nitrogen use efficiency and reduce the impact of nitrogen use on the environment and water quality, I got to manage what, how, where, and when I apply it through the growing season. Because I know if I over-apply, I'm going to lose it. Okay, anyway, that's the infiltration runoff issue. High infiltrations just start raining, it's all going in. I got no runoff. But when the pores fill up, I can't get any water in there anymore. The pores are full. It's still raining. That's when you shut your irrigation system off. Pores are full. So if you have any kind of slopiness to your whatever you're using, well, you know you're going to get runoff. And if I just let it go, I get lots of runoff. Don't do that. Don't do that. The flood, you're old enough to remember the big flood in '99 and the one we just had in '18, yes?
Yeah.
Well, our soils were saturated in both of those events. I loved it. The press calls them 500-year floods. One was in '99, one was in 2018. My math says, anyway. In '99, we had 4 hurricanes hit that fall. You recall? It was actually 3, but one hit us twice. It came and hit,
That's right.
went up to New York and came back and got us again. And when it got, all of the soils were saturated and that water couldn't get in. And so all that runoff and we had floods. Poor Princeville took it really, really hard. Anyway, okay, now real quick comment about soil health. You got a section coming up on composting. It's very important if you have a small area the size of this room or 3 or 4 times the size of this room, you can increase the organic matter content by importing more carbon than your plant residues produce and leave behind. So you're going to want to try to grow that organic matter by adding more carbon. So just really quick, this is what I was talking about. Old farmers, in their practices over 100, 200 years, this topsoil, the O and A horizon, they're gone. This is what we're farming because of all this soil erosion, et cetera, et cetera. And then we do some things now that we'll bring it back. But it took 50 years to reduce the organic matter content by 50%. Only 50 years. It'll take a couple hundred to bring it back. Now we can bring it back, and major issue in Africa and sub-Saharan Africa where the population growth rate is one of the highest on the planet and their soils are so impoverished, it's really a challenge for those folks to feed themselves. Anyway, degradation of our soils is because of physical soil loss. I turned that off. And then this oxidation of the organic matter. Let me just remind you that, again, all over the planet we've measured this effect. 50% loss. This study I worked in when I was in Kansas. It says this is 100% of the original organic matter, virgin soil. That means it's never been touched by humans. Never tilled, nothing. And how long did it take me to lose 50% of my organic matter? 50 years. Now, in a harsher environment, it only took 30 years. It took 30 years to lose 50%. And Oregon is a pretty mild environment. It took a little longer. But on the average, 50% loss of 50 years. Anyway, so there's my virgin organic matter. Your gardens aren't like this. Your gardens are like this. But when humans first started scratching the soil surface, we lost that topsoil. And now we can bring it back. So NT is no-till. Don't stir it up as much. All kinds of best management practices. Maintain a good rotation. And then if you really want to move it up faster, cover crops, compost, buy any carbon source you can find. The cheaper the better, right? Find free carbon sources if you can. Sawdust is great, but sawdust has problems. Pine needles are great, but pine needles have serious problems. Leaf waste from municipalities is a great source of carbon, but they have problems if I apply too much of them. So you got to have a waste analysis report. So I'd have to come back and show you how to interpret that report. So again, it's the biology that you're trying to do. The soil is alive. Never forget that's a living, breathing organism under there with billions and billions and billions of different kinds of bacteria, macro and microorganisms. It's alive. And we farm it. It's not fertilizer, didn't kill it. We killed it because we destroyed that valuable O and A horizon. So there's less life in our soils when we find them than what our predecessors found. And your goal is on your plot of land is when you leave it to whomever, make sure it's more productive than when you found it. And we're good to go. Anyway, I'm going to go by this because we just don't have time. Healthy soil. You heard that soil health term a lot, right? We used to call it when I was younger soil quality, but that didn't ring a bell with folks, and so now we call it soil health, but it's the same thing. So if I want to enhance my soil's ability to grow plants and be alive, I'm going to maintain surface residue cover. I'm going to have rotations that leave lots of stems and straw behind, lots of roots, and none of this. Keep your soil in place and figure out how I can increase the amount of carbon input. More carbon going in than carbon loss. And this is my one phrase that works, keep the soil covered year-round. Don't let it sit there for 3 months bare. That's the worst thing you can do for the life in the soils. Keep it bare. So keep it covered. If there's a non-crop period, plant some ryegrass or some kind of cover crop. Keep it covered. Or put a mulch over it. Buy some carbon and put a mulch over it if it's not live. Dead or alive, I don't care. All right, you get the idea. All right, so let's go back to this because we got to finish this up. We're good. We're on target. Anyway, you saw this before. All right, so this is all the nutrients.
You want it? All right.
Do your thing, man.
All right, there's a simple way to remember all of these. All right, so I'm going to give you 6 words.
Time's up. No, go ahead.
There's 6 words. If you write them, it'll be great. Okay, the first word is C. Before you do that, they're all the initials of the elements.
So
Okay,
C
C is carbon. All right, so the 6 words: C, carbon. Next word is Hopkins. Hopkns. Hopkins.
Phosphorus, potassium.
Right. Next word is cafe. CAFE. Calcium and iron. Next word is magnesium. Well, MgB. Okay. Next word is MnCuZn. The last 3 words would be Cl, Mo, and I. So if you remember it, it's C. Hopkins Cafe, managed by my cousin Clyde, Mo, and Nick.
Oh, mighty God.
Oh yeah, but it's,
I've been doing this for 40 years and I still don't remember that.
So it's an easy to remember all 17.
But here's the, thank you so much. Here's the bottom line is, our acid soils, our ultrasols, we know we got to have nitrogen unless I got a legume in there, right? And I need potassium, I need to make sure phosphorus, magnesium, calcium is generally not deficient, it's rare. On peanuts, we add extra calcium. It's a dose of gypsum that we add to peanuts. Peanut producers already know that they've limed their soils up to 6.5, everything looks good, pH-wise, lots of calcium. But they add another 1,000 pounds of gypsum to make sure just before it starts to peg. Anyway, sulfur, very rare, very rare. On our sandy, low organic matter soils, we can. But if you're irrigating, then guess what you're doing? You're adding something to your soil. And you're going to say, well, it's just water. But it's not just water. What's in the water? Cations and anions. Don't you think you ought to know what's in there? Now, if it's city water, a lot of that stuff's been removed. You still have calcium, magnesium, and it's not very high. But if it's groundwater, you really ought to know what's in there. Sorry. Anyway, so get a water analysis. Send in a jug of water to the lab and get a water analysis. When I got to North Carolina, I asked this question, and the lab, we have some irrigated producers in North Carolina, quite a few actually. And they didn't have any data, any irrigation samples that they could share with me. The data, not the water. And so we went to some irrigators and had them sample and sent it in the lab, and one of them had 34 parts per million sulfur in it. And if you add a foot of water, that's 45 pounds of sulfur. And the plant only needed 15 to 20. So you got a salesman walking around saying, I think you need to buy some sulfur. And you would not know if you didn't do that analysis and do the math that calculates how much sulfur you're applying by how much water you apply. And it's a really simple math. We can't go through it today, however.
What about rainwater?
Rainwater's got very little in it, but it does have cations and anions in it, and it has a pH. Our pH of North Carolina rainwater is 4.6. Unpolluted rainwater is 5.6. So we have some pollutants, mostly nitrogen and sulfur, that add a little more acidity. There's very little calcium, magnesium, potassium, those mineral nutrients in our rainwater, but there is a little in. If you do the analysis, there's a website called I'll get it here in a minute. Old age just hit me. National Atmospheric Deposition Program, NADP. Just Google NADP, it's the first thing that comes up, and you get maps, and they sample stations all over the United States, and they figure out what's the pH of the rainfall, how much sulfur, nitrogen, calcium, all the stuff that's in there. And you can get a distribution. North Carolina, in the Northeast, before we start taking the sulfur dioxide out of the flue gas from burning coal and oil, we had a lot of sulfur, and pHs in the Northeast were 3.5 rainfall. So a lot of our freshwater lakes were dead because of the acidity. It doesn't make our soils very acid because it's not that much rainfall, not that much acid that's being added. It's the sulfur that we're adding. Now we've taken that out. It's one of the greatest environmental success stories on the planet is the United States removal of sulfur from its flue gas. And the pHs have gone from 3.5 in the Northeast to 4.5, 4.6 in just a matter of 20 plus years. And it's dropped, continued to drop. Anyway, we're seeing more incidents of sulfur deficiencies in these areas that have less sulfur in the rainfall. So yes, rainfall does have nutrients, but not many. So the rest of these, don't worry too much about those. But if you have a soil test, they'll tell you. I'll show you, go through that here in a second. Iron, forget it. You don't even see iron on the soil test report because it's so concentrated. Our acid soils make it so soluble that it's loaded with iron. And so you never need iron, ever. That one you just take off the list. And I don't know of any plant that's so sensitive to iron that you need, you plant that one plant that's going to be deficient. There is no such plant that you could grow in North Carolina soils to be iron deficient. Chloride, forget that. And nickel, forget that. So, all these others. There are certain crops in the coastal plains, some sand and some organic soils. Copper can be a problem on our heavy organic soils. You don't have those kind where you're in this region. They're the muck soils in the east. Boron. The wine grape growers always put a little boron in their fungicide sprays. Why do they do that? Because that's what they do in California. And so we did research and found out that our plants are pretty well endowed with boron. So it's a wasted application. But it doesn't cost much, and they feel better about it, and so let it go. All right, so plants take nutrients. When they take the water, we already talked about the water, the nutrients are in the water. Now, plants don't have a brain. They don't say, well, I need some more potassium, so let me take in a little more potassium. All these cations and anions are dissolved in the water. Okay? That's how the plants get them. They take them in. And once the plant removes that water and you've harvested your crop, then the soil replenishes itself. Not always if you never replace some of these nutrients over many decades, while your soil will become impoverished. with some nutrients. And so what are the factors, what are the components of a soil that replenishes the solution for your next crop? And that is, number one, and most important, is organic matter. So the more organic matter you have and build up, the more nutrient supply you're going to have. That's a good thing. Plus your soil is more alive, there's greater infiltration, all kinds of soil health factors that are important besides the nutrients. Cation exchange, we're going to talk about that here in just a second. Those are the clays that have cations held to them. You probably know about that, cation exchange. And then there are solid compounds in the soil that slowly dissolve into their cations and anions and pump some of those into the soil solution. So soils do regenerate nutrients, but if I don't replace what I'm removing, that can be a problem. So how do we know? We soil test. There's a system. Take a sample, blah, 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 and you need to do that every 2 or 3 or 4 years. You need to sample it the same way every time you go sample it. Don't change the way you've sampled it. So if I got a field over here, and I'm going to show you an example, it's a different soil in that corner than it is over here, I'm going to keep those separate. Because one year, if I've got a large field, you have a large acreage, right? It might be Friday afternoon at 4:30 and I got something to do at 5 o'clock. So I run out that corner and take my soil sample and I forget this out here. And that sample is useless. So sample it the same way every time is the key. So again, if I have a field, you can kind of see what I'm doing here. I'm dividing, if I have any slope. If you have small acreages, then you're maybe pretty flat. Don't worry about this too much. One sample would be okay. Unless my rotation is different in different parts of my garden or my area, then I'm going to sample those separate. I'm going to mark them, make sure I know that this is a rotation that's a little different than this one over here, because I'm managing these things differently. So I need to keep those separate. Anyway, develop a plan. Your agents can help you with that, or we can get together and do that. I'm going to just quickly say we are going to define what this is, called a critical level. It's a critical soil test level below which my soil test report says it's below that critical level. I have got to apply that nutrient somehow. Organic, inorganic, manure, fertilizer, bad, I don't care. I need to apply that nutrient. And so in your soil, if you find your soil test way below the critical level, I need to build that up. So I'm going to apply a little more than I might export by my crop to get that soil test level up here. Because the research says that anytime I have a soil slightly above that critical level, I always have my highest yields. But if I have a field down here, I might have applied enough phosphorus to optimize yield, but it's still not as good, continues consistently as when my critical levels are up here. So I'm building it up, but at some point I don't want to keep building it up to, too high. I don't want to do that. I want to then maintain it just slightly above the critical level. And then when I get up here, I can say, well, I can stop fertilizing for a while. Guess what's going to happen? It's going to go back down. And so I got to resample every 2 or 3 or 4 years just to make sure where I am on that curve. And I save my data every time I pull it out. All right, so I'm going to take it to the lab and I get this report. And you look at this report and you go, ugh. All right? So in the next half hour, a little over, I'm going to explain every number on this report, and you're going to walk away with an understanding of reading this report. Now, if I don't send, this is an NCDA report up here. If I don't send it to NCDA, you send it to Waters Lab and just say, I want a North Carolina report. And they give you a North Carolina style report. Okay? If you want the data back in 3 or 4 or 5 days, you send it to Waters Lab. If you want the data back in a month or 2, then you send it to NCDA. And you know what? NCDA won't send the sample back? Go give me the results in 3 or 4 or 5 days? No, because it's a government lab. What do you expect? I'm serious. It takes forever. And if you need to make a decision in a couple of weeks, you're not going to have the data. and don't make decisions without the data. So if you're late and you forgot the soil sample and get the numbers before you go buy stuff to put on your garden, send it to Waters or send it to another commercial lab. The price is not bad. It's like $8 or something like that. And NCDA during the busy season is $4 or $5 a sample, so it's no big deal. Anyway, so I want to tell you the first number I have circled is HM. That's organic matter. They call it humic matter, but that's the organic matter content. In your soils, if you've not amended it like I've suggested, that organic matter content is very low, less than 1%. Less than 1%. I'd like to see you get those up to 3 or 4%. And now your soil is cooking, alive. Anyway, for you folks in gardens, you'll get this horticulture report. It's the same numbers, but they've left some good numbers off. Because they don't think this is, you can interpret that. You're not smart enough. But you are. And I'll prove that to you here in just a minute. You are plenty smart enough. But I can get, if you send in, I'm a garden sample, that's the report you'll get automatically. They don't even give you a choice. But if you send in a sample, say, I want an ag sample, you get this. But if you get this, you can go to their website and enter your sample number, your PLO, PL, whatever the number, I can't remember what they use, on their website, and you get a spreadsheet, and you get all the data. It's just in this form. Cute little graphics on pH and P and K. So you don't have to worry about the numbers. I think you ought to worry about the numbers, and that's what we're going to do today. All right, so let's go. In 10 minutes, you're going to have these 6 numbers. That's 6 out of about 14 numbers. So over a third you're going to have in just 10 minutes. Ready? All right, first one, cation exchange capacity. What is that? Well, that's my clays that are charged, negatively charged. That's the little dashes. Negative. And my cations are positively charged, so they attach. So on the surface of my clay, I have as many positive charges as there are negative charges. The size of my cation exchange capacity, the amount of negative charge on my clays, is equal to the number of positive charges stuck to it. Can't be more, can't be less. So what we have to do is figure out, well, what's the distribution of the good guys, the blue ones, and the bad guys, the red ones? That's really important. Understand the distribution of those cations. That's the soil test report. So let's go to the next. Now again, remember, the more clay I have, the more CEC I have. So your CECs are generally 5, 6, 8, 10, 12, 14. Sands are 1 or 2. The more clay I have, the more more organic matter I can bring in, my CEC really goes up. Because organic matter has a high cation exchange.
Where do you want that CEC to be ideally?
It doesn't matter. Just know that you're going to have a CEC, and what you're doing is managing the distribution of cations on that CEC. You're going to see that in a second. It doesn't really matter. One soil with a higher CEC is not better than a soil with a lower CEC. But the distribution makes one soil better than the other. Okay. So, here's my cation exchange capacity. Right? Can you see my weird graphics? There's my clay. All the little negative charges, and there's all my cations. So quickly add up the charges. No, don't do that because it's too complicated. So I'm going to separate them into the good and bad guys. How many bad guys do I have? Huh?
4.
Charges.
12.
12. Very good. See?
Say charges.
You're right, I did not. How many charges of the good guys do I have?
12.
Yes. So what's my CEC?
0. 1.
No.
1.
The cation exchange capacity is the amount of negative charge that's equal to the amount of positive charges that are on there. How many total positive charges are there? 24. My CEC is 24. Yes? Yes?
If you say so.
Well,
Well, how do you know what the negative charge is?
there is no negative charge because the clay is all negative.
I got you.
There's no anions that could be attached to a negatively. It's like a magnet. I got a negative end and a positive end. If I got a negative end, there's no anions going to be over there. They repelled. Okay?
Bases plus acids equals the CEC.
Yes. So let's just do the example here. I got 12 bases. I got 12 acids.
How do you get that?
Huh?
I'm sorry, but how is the bases equal 12, but the 4 acids also equal 12?
Because each one is plus 3.
Look at your charges.
Right.
Look at the charges. That's a plus 3.
That's the number you
Yes.
Yes,
Okay,
yes, yes.
Sorry, I missed
No,
that.
no, it's all good. It's all good. It's a little funky at first, but you'll get used to it, right? All right. So, the second term on your soil tester's report is called base saturation. BS percent. Remember that it's not the quality of this presentation. What is the percentage of the total that's occupied by the bases?
0.5.
50%, yes. Not half percent. 50%, yes. Wish I had some cups or hats to give out. Well, it doesn't, but in this case it is. What is the percentage of the CEC that's occupied by the acids? Okay. 100% of the CEC has acids and bases on there. And the distribution is 50-50. Is it always 50-50? No. The soil test report. What is it on that first sample?
This one doesn't have a BS.
Thank you. I need you to look at these. Don't look at that yet. 60. Yeah, sample A. We're looking at sample B, actually. We're looking at sample B. 73. What's the acid saturation percent?
1.6.
No, that's the AC.
Oh, that's
73%. So how many what's the percentage of the CC it's at? 27%. Always has to add up to 100%. If my base saturation were 80, my acid saturation would be 20. If my base saturation were 20, my acid saturation would be 80. That's it. 2 parameters. Base saturation. That's pretty cool. So, base saturation is the sum of all my bases. Calcium, magnesium, potassium. Out of the total. So in that, this is sample B on your handout. 73% of the CEC, 73% of 6 is how many bases I have. Yes, 4.2. Now, this number is not the percentage of acids. This is the acids. It's how many acids. And you just told me that the percentage of acids was 27%, right?
Yes.
So guess what 1.6 divided by 6 is? 27%. They don't give you the percent acids on the soil test report because you know you can subtract the basis percent from 100 and get that. You can do that in your head. They put the AC on there because that's the parameter they use to make the line recommendation.
So AC stands for acid,
It's number of acids in the same unit.
so it's the number of acids.
Yes, it's the same units as CEC. So if I divide, I'm going to show you that in a minute. Gosh darn it. AC is the number of acids. This is on your handout. If I take the AC and divide it by the CEC times 100, I get the percentage. Now, they don't list the percentage of acids because you can do that in your head. We just went through 3 examples. So, here's the relationship you just told me you understood. Yeah. I'm trying to get you now to interpret the base saturation percent relative to pH, which is the fourth term on your list. So it says here's pH, and here's the percentage of bases or acids.
Right.
So at pH 7, at pH 7, what is the percentage of bases?
100%.
What is the percentage of acids? It has to be 0. They can't be more than 100%. Got it? Okay. Now, what happens if the pH goes down a whole unit? Now I'm at 6 pH, and the base saturation percent is 80, and the percentage of acids is 20. I think you have it. And at pH 5, what am I? 50-50. So when I take a soil sample and I send it to the lab and I come back with pH 5, you can look at the base saturation percent, and it's probably not exactly always 50%. Soils are highly variable, but it's pretty close. And it says I need to add some lime. It says I need to raise pH from 5 to 6, which means I got to change base saturation from 50 to 80 and lower acid saturation from 50 to 20. That's it. That's it. So, you now know that as pH goes up, my bases go up, my acids are going down, right? And these are my bases, so these guys ought to go up. What is the calcium-magnesium sum right there? What's the total of those two? 69. What's the base saturation percent? 73. They're not quite the same. What am I missing? I'm missing potassium. So there's 4% potassium, right? 73 minus 6. You don't need to know the percent potassium because the potassium on the soil test report is given as a different kind of a number. It's not percent. Don't worry about that. I'm going to cover that in a second. Don't worry about that. I'm just want you to know that as base saturation goes up, these two numbers are going to go up. So let's go through the optimum pH, depending on your crop. I like to see things around 6.5, 6.8. 0 to 8 inch sample. Unless you're growing hydrangeas, azaleas, and blueberries, and several other crops. Longleaf pine. Don't be liming those crops. You'll be very disappointed in your blueberry production if you start liming your blueberries. All right. Let's see. I gotta go through something that I'm sorry about this, but there it is. I'm gonna go through this real quick. I meant to put this up earlier. All right, let's go through sample A. You got sample A. What is the pH? 5. Okay, what did we say pH 5? About 50-50. Bases and acids? What do I got? 62. All right, that's not 50, but it's what's the acid percent? 38. Very good. Yell it out when you know it. All right, how do I get 38? I took 1.7 divided by 4.5. That's 38%. All right, what's the sum of my calcium magnesium?
60.
60. Okay, let's raise the pH from 5 to 5.4. What happened to the base saturation? It went up. pH went up, base saturation went up. The 1.6 divided by 6 is now 27%. The acids went down. What happened to the sum of the calcium magnesium? We already said that was 69. So that went from 60 to 69. That went up. Let's move the pH up even higher. Now I've got pH of 6.2. What's the base saturation? 90. What's the acid saturation percent? Again, it's not on the report because I can do that in my head. But if I wanted 90, I just take the AC and divide it by 12.3, and I get 90%. 10%, sorry, 10%. Thank you for correcting me. Did the calcium magnesium go up? No, that's 90%. There isn't much potassium. And look, that's a really low number. That soil is potassium and phosphorus deficient. We'll go through that here in a second. And let's raise it up to pH 7. What's the base saturation? 96. It's getting to 100, close to 100, isn't it? And my bases, calcium, magnesium is 93. So I got 3% potassium. My acid, 0.6 out of 14, is 7%. You now have 6 numbers on that soil test report that you're now intimately familiar with. Okay? All right, so the question is, well, we got to go back. The question is, what does all this mean relative to this management decision you all, unless you're blueberries or azaleas, I wrote that out, you all will be doing, and that is adding lime. There's no free lunch with this guy. So you get a lime recommendation on your soil test report. Get a lime recommendation. Clays are usually, my pH for sand and clay is 4.5. If I want to raise it to 6, I'm going to have to apply about 7/10 of a ton. If it's a clay, I get almost 3 tons. Okay? I'm going to show you where this comes from here in a second. So, what happens when I add this miracle product called calcium carbonate or lime to my soil? Now, here's where some of the chemistry comes into, but you can know, this makes sense. This is my CEC with aluminum. I've taken off the bases, but I need to get rid of some of these acids, right? So I add this base. It dissolves into that cation and that anion, and so I need 3 of these. 6 charges will knock off 6 charges. Yes? 3 calciums are needed to remove 2 aluminums. 6 charges changes 6 charges. Okay. So let's do it. Now I got the aluminum in solution. All right. So here's the liming. Remember our problem. 50-50, pH 5, yes? Okay. I want to take it to pH 6, which means my bases are estimated to be 75%, my acids are 25%. So I got to get rid of 2 aluminums, right? 25% of the CEC have got to be changed from aluminum to base to calcium. And so why do I have you in the back that has a sandy soil and you have a clay soil and your neighbors? You're down here in the bottom ground, sandy, alluvial sands, and you're up here on the hilltop and you're clay. We both have a pH of 4.5. But you have a recommendation of changing my lime pH from 4.5 to 6. You have a recommendation on the sand of only 1 ton, but the guy at the top of the hill has a recommendation of 3 tons. And the first thing you do is go to the lab screw up. Bless you. Lab screw. The lab didn't screw up. The lab did exactly what they needed to do. Again, when I have a higher CEC, 50% of 10, 50% of 20, is how many bases? 10. 50% of 5 is 0.5. 2.5. 50% of 5 is 2.5. 50% of 20 is 10. I got 10 acids I need to get rid of. I got 2.5 here. So my lime rate is bigger, higher for a clay. So you got your clay soils, don't cheapen up on the lime. Don't skimp on that lime. It's really important. All right, and why is it important? This is our wine grape work. That's wine grape plants, pH 4 to pH 7. And there's the roots. It's important. Okay, so I'm going to move on now. Your lime recommendation on your soil test report, this is a really important point. Circle star this slide. Don't forget that when I see the lime recommendation on the soil test report, it is pure lime, pure material. When you go to the lime store, it's not pure. So I gotta know how pure is it. And the label, law requires the label to tell you. So if I have a recommendation that says I need to apply 1 ton of pure lime, that's what's on the soil test report. They don't know what product you're gonna buy, so they have to assume pure lime until you make the adjustment. And it's only 50% pure. How much product do I need to apply? Twice as much. Twice as much product. If you use and buy a product that's 50% pure and only apply 1 ton, your pH is not going where you think it is. Okay? They're very, yes ma'am.
With the lime products that are 50% pure, what would the other part of it be? Is that something?
Not counted as a salt or a compound that will neutralize acid in the time frame you want it to. Okay? This lime, it's not anything else, it's not garbage, it's lime, but the particles are so huge they won't dissolve in time. Now, most products that you find in the marketplace are down here. So you won't find a 50%. But if you go and use wood ash, it has a liming value, and it's not 80%. And so you got to have the liming value from that wood ash, and that can be obtained from your agent. Anyway, you find either 2 choices. This ag lime, it's just rocks ground up at various fineness, and you got 2 choices, calcium or one that has calcium and magnesium. So if my soil test, can you look at the soil test and see the percent magnesium?
Yes.
If it's 4% or less, that's a red flag. That's a red flag. 4% or less. You see 4%? You don't see. They're all in the 20s, right? These are good. They're good to go. You can use calcium carbonate. But if that magnesium percent is 4% or lower, then you try to find a liming material that's got some magnesium in it. Okay? Guess what's not on, you have this. Guess what's not on this report?
Magnesium.
You don't see that.
No.
And I've asked the lab 100 times, put the magnesium calcium percentage on this report so we can determine which lime product to buy.
Who do we rate?
And they haven't. Takes government a long time. Anyway, the other product is called pelletized lime. And all that is when they crush the rock, you can imagine it creates a lot of dust. And the dust is really fine material. It floats in the air. So they suck that out and save that. That's the finest, most reactive particle size there is. They mix some compounds, some plastics, soluble plastics with it to make it into a pellet, and it immediately dissolves. And it reacts really fast. So if you want your pH to change in 2 or 3 or 4 months, pelletized lime is the way to go. That's more expensive, not by much, but it is more expensive. But it'll change your pH, boom, 3 or 4 months. Ag lime sometimes can take 12, 15 months for it all to react. Okay. So let's quickly go through this. I'm going to pass this up. I'm going to give you an example in a minute because we're running out of time. Don't worry, don't worry. This is the particle size. It's on the label. I'm going to show you a real live label and do the math that I just had on there. Real live label. Can you see the difference in particle size? 200 mesh. Now what's a mesh? A mesh is the number of crosshairs of my screen. Your backdoor screen. It's like how many crosshairs in an inch? Probably 15, 10? Right? If it was 8, a mosquito would get through it. Okay? But if it's 20, it's a gnat would get through it, but all right, you got the idea. So the finer the particle size, the faster it reacts. So there's the soil pH. I'm adding the same amount of lime, but here's the pebbles, and it didn't change pH much. There's finer material, changed it, but it took a year and a half. And there's finer, it took about a year. And then, by the way, this one didn't even get up to pH 6. And then I got pelletized lime, and man, it went right up in 6 months. Boom. But it's going to cost you more because it took more energy and to crush it smaller. Anyway, you get the idea. Ag lime. Do not put ag lime in one of these whirly-gigger spreaders. You will be very upset. Have anybody tried that? Yeah. You didn't go down through the holes, did it? Oh, yeah, you had to dig it out of there with your hand and then ended up spreading it by hand anyway. Pelletized lime go right through. It's easy to spread, pelletized lime. Okay. So, I found this product by a grower, vineyard grower. I'm going to give this example, and then we're going to do the soil test, P&K, and micronutrient indexes, and then we'll be done. Okay, so we're on schedule. I did this calculation a few slides back that I passed over, but I'm going to do exactly the same calculation with this example. And the reason why I want to give you this example, because this product is being marketed in North Carolina, and I'm happy to have you buy it. It costs 3 times as much as ag line costs. But they tell you that I only need 25% of the recommended amount with my product. Isn't that 25%? If I'm putting 200 pounds of pelletized lime on, if you buy this stuff, I only need 50. And so an elder lady built 5-acre vineyard out west, Yadkin Valley, and she'd heard all my presentations with the wine grape growers, and she was getting ready to buy the lime, and the salesman came along and says, buy this. It's only 3 times the cost, but you only use 25%. So you're ahead, right? So she did. She bought it. And she was smart enough to go back the next year and soil sample this little teeny vineyard and measure the pH again. And guess what? Happened. pH didn't change. The pH didn't change. pH didn't go up. It should have. And so I want you to be able to understand why it's important to know this stuff about CEC and base saturation. And when you make this decision, you can sort out crap material from good stuff. And all you have to do is have the label. Yes, ma'am?
Was it because it was liquid? It
No.
washed right through?
No, I'm going to show you exactly what the problem was. So, we go and look at the label. So, in North Carolina, any particle that's bigger than 8 mesh, don't write this down. Don't write this down. Any particle that's bigger than 8 mesh, you give no liming value. This is calcium carbonate. If you can imagine oyster shells, that's calcium magnesium carbonate. You grind them up like flour, that's a good liming material. But it would take an awful lot to grind them up like flour, right? So you take a little hammer and you beat it up into BB-sized particles, and that's 8 mesh. And it just won't dissolve fast enough. The surface area is too small. Not enough reactive surface, so it just sits there. Now, it eventually will dissolve, but you and I won't be around when it finally does. Okay. 8 to 60 mesh, that's a finer particle, right? It's the stuff that fell through the 8 mesh screen but stopped at the 60 mesh screen. It's a medium-sized part. We give those half value. But anything that falls through the 60 mesh screen, which is the finest stuff, we give that 100% value. So this label says, I have 100% of material fell through the 8 mesh. It's all. 5% didn't go through the finer screen. It was held on top. So this 5% of my product is only worth 50%. All the rest of it that fell through is good to go. That's 100%. Now, they also give this value, and this says 91%, this is the source. It says calcium carbonate. I need this number, and I need these numbers to calculate this number. So let me just do that for you real quick. The number you're looking for on the label is this thing called the effective calcium carbonate equivalent, the ECCE. It's on the label. It'll give you, it's in percent. It comes from me multiplying the source of the material times how finely it was ground. So let's use the label and go, okay, remember, there was none of it that, all of it fell through the 8 mesh, so there wasn't any big chunks. So that's 0. And this is the percentage that's available. And there are 5%, remember 95% fell through the 60 mesh. And so 5% is half available, 50% available, so that's 2.5%. All of the rest of it went through, and that's all available. So you add those up, and I get 97.5% fineness. And I multiply that fineness number times the value of the source that's calcium carbonate. So let's do that. Again, the calcium carbonate equivalent is 91. Here's all my fineness factor data. And I got 91% off the label times the 97.5% I calculated. And the value is 88.7 or 0.887, 88.7%. Now let me go back real quick and show you that they said effective neutralizing value is 88%. They admit on their label that this stuff is only 88% pure. So how much do I need to buy if my recommendation is 1 ton? They said if I buy 1 ton, all I need with this product, all I need is how much? 500 pounds, right? Right?
Yes.
Okay, good. So let's just find out. I got 2,000 pounds, 1 ton. I divide, which means I gotta have to add more than that. I need 2,250 pounds, not 500. And that's why the pH didn't move. And I've called them. They don't like me. They don't like me. And they say, well, you just don't understand the man. So but at that point you can't negotiate with them because they're not in a position to budge. It's kind of like politics. Anyway, another one out there. It is 10% calcium, and they'll say, well, calcium's a base. Increase the base saturation. Increase the base saturation, your pH is going to go up, right? Well, not unless you neutralize the acid. And chloride won't do it. You got to have carbonate. So you're adding calcium, but it's never going to change the pH. Never, even though they said on their advertising it will. So again, here's the reaction. Calcium chloride plus the acids. I still have the acids. They're still there. They didn't go anywhere. So be careful. It's not a liming material. I need a material that has this carbonate, combines with the acids, and turns into water. I win. All right, so again, be careful. There's all kinds of crap products. The biggest one that I know of for increasing the soil life is humic acid. I got a jug, cost me $45-50 in a gallon, or 2.5 gallon, I don't remember which, and they say it contains 0.03% humic acid. That's organic matter. Or 0.3%, or 1%, no more than 1%. And you put this on there, and your soil just goes crazy. Well, go ahead and buy a gallon and see what happens. And you'll find out that it's a waste of money. Okay, the rest of the soil test report. Remember, we got 6 of them done. All I need to do is finish these. And this goes so fast that we're good to go. These are called indexes. All I need to know is what the critical soil test index is. And if it's above that number, I don't worry about applying that nutrient. If it's below that number, I need to apply that nutrient. If it's really low, I need to apply more, and if it's not much below it, I need to apply less. So let's just take a peek. the whole idea of a critical level says that if I have a critical level, there's my soil test value, and I'm going to categorize it as high or in that neighborhood. That means the soil is providing 100% of what my plant will need. But as the soil test number goes down, then my soil's contribution to meeting the nutrient demand is lower, 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 and I need to replace that lack of ability of the soil to meet that nutrient requirement with added nutrient. So I just got to know what that number is, and then figure out, well, if I'm here, I need to add, my rate should be higher. If I'm here, my rate's just a little bit. That's it. So in North Carolina, on your soil test report, let's take a peek at this guy. Let's use the garden one. What does it say for PI?
19.
Yes. But what does it say it should be? There's two vertical lines. 50 to 70, right? Yes?
Yeah.
And it's 19, which means it's really low.
Yeah.
So I'm gonna get a pretty high P recommendation. I suggest that you keep your soil test values at or slightly above 70. If it was 100, I'd be happy. That's slightly above 70. Okay? Now, if you call the lab and say what's a critical level, they'll go 50 to 70. And that's right. I like to keep it at the upper. You know why I do that? Because I've taken an average soil sample, right? I've taken 10 cores, put it in a bucket, and that one number represents my entire garden area. And over there in that corner, it might be 30, and over here in this corner, it might be 90. On the average, it's 60, right? So average values sometimes can be misleading depending upon the variation in your field, your garden, and what numbers made up that average. I could have an area that's 300 over here and only take the cores over in this spot, and I wouldn't get a recommendation, right? But down over here in the corner might be 10. And if it's the same amount of area, 10 plus 300, why, the whole field would come back and it'd say it'd be fine. When it isn't. That area right there needs a serious amount of phosphorus. So I try to keep my average soil test values up at or slightly above 70 to account for that variability. Anyway, that's for P and K. Sorry, that's for P and K. They're the same index, okay? All right. Micronutrients, 25. I usually try to shoot for 30. Don't worry if you don't. Most of these are not needed. As I already said, they're rarely deficient in North Carolina soils. So I just now have determined almost every data point on that soil test report. So remember, when you have a garden soil test report, you don't have magnesium. So you got to go to the spreadsheet output from the lab, use your number, and it says, well, how do you want to see this? PDF, you get this. If you say Excel, click on Excel, you get the whole spreadsheet, all the data, and it'll tell you percent calcium, percent magnesium, and you can determine whether you need dolomite or calcitic lime. Anyway, we're out of time. You're not going to use tissue analysis much in your gardens because if you see a symptom, it's too late. It's too late. Unless your plants are pretty small, you can adjust. But if your plants are growing and your fruiting stuff is happening and you see a visual symptom, it's too late. But it'll tell you, well, maybe I'll do a soil analysis and figure out what to do so I don't have that next year. Anyway, we can come back and work on that. I got some more handouts. I wanted to just pass them back. Oops, sorry. What this is the lab will tell you should apply 15 pounds of 25 pounds of 15O, I used the example earlier, 9 per 1,000 square feet. And you go to Home Depot, you don't see 1509. You don't see that. They're coming. They're coming. Extras in the back, slide over to the middle row, would you, please? Did we run out? Shouldn't. I had 40. 5.
Here's people in the middle row.
I will send all of the handout materials, and you can get. All it is an example. I have ones that aren't filled out for those of you. But you'll go to Home Depot with a 4 pounds of N per 1,000, and this calculation will tell you, okay, I found 12, 5, 7. Is that what it says? The first one? It's right here. Yeah.
Right.
How many bags do I need to buy? Well, what did we find? How many bags? 3/4 or 2/3, right? What's it say? Point something bags.
0.67.
2/3 of a bag. Well, you can't buy 2/3 of a bag, so you buy a whole bag. And what do I do with the third? Don't save it. Go take that third of a bag and throw it around your landscape plants. They need nutrients too. Especially if you use pine needles as a mulch. Because those trees and bushes and shrubs are starving for nitrogen. So do that. But if you're organic and you want to be certified organic, you can't use fertilizer, right? Even though urea is an organic compound. Let's not debate the insanity of the organic regulations. But there's the composted cow manure. How many bags of that do you need? 8. Well, you're not going to Home Depot in your Prius and buying all those bags, right? You need a pickup truck. Okay. Sorry we didn't get through all of it, but we can come back and do some more.
Dr. John, thank you.
That's okay. That's okay. All right. The last slide, by the way, is my contact, and I do give you my cell phone. So if any of you have a problem or an issue, I won't answer my phone because I won't recognize your number. But if you leave me a message, I will call you right back. Yes, all my students have my cell phone number. Because they can, so I mean, I don't want to be the limit of their learning, so that their access to me is important. Okay. All right, very good. Good luck. Have a great season.
Thank you.
Sorry, I went 2 minutes late.